SwayamPrabha. Digital India. Educated India.
Good morning and welcome to this next lecture on vibrations of plates and shells. We are in the topic of receptance, dealing with connected structures. Okay. One thing I wanted to mention is here. So this was a simply supported plate connected to a spring. And this was the new frequency equation. Okay. So let's see if I can remember 4 by rho h a b. Okay. So we had this equation. Four by rho h a b sine square m pi x star by a sine square n pi y star by b divided by omega mn minus square minus omega squared and a double sum over mn plus 1 by k equal to 0. Let me just check once. Okay. Now we have seen the details of this in one of the earlier classes. Okay. What I just want to mention is, suppose k is small, k is a small quantity, okay, a light spring. Then chances are that each of these new resonances are slight perturbations over this. Okay. That means around or close to each new resonance omega I nu, then omega square mn minus omega I nu square will be a small quantity, which means that term will dominate. Around each omega I nu, this term will dominate because it is in the denominator. And so we can come up with an equation for I nu. Okay. So the summation is no more needed because omega I nu is close to one particular omega mn. So we will have 4 by rho h a b sine square m pi x star by a sine square n pi y star by b by omega mn square minus omega square is equal to minus 1 by k. Okay, and this is I nu, let me say I nu. Okay, then we have let's see, 4 by rho h a b sine square into sine square is equal to minus omega square mn by k plus omega I square by k, which means omega I nu square, particular fellow, okay, is given by 4k by rho h a b sine square plus omega square mn. Okay, a particular, let us say omega m is 1, n is 1, omega square 1 1. You put m equal to 1, n equal to 1 over here, that is the perturbation to omega 1 1. Okay. So, omega 1 nu will be a perturbation, omega 1 1 plus something small quantity. So, there is a quick formula here when k is not significant and it just slightly modifies each resonance. Now, last class I said we are going to look at this topic of stiffening of a cylindrical shell. Okay. So, stiffening of a cylindrical shell. Now, stiffening can be done to strengthen, okay, stiffening can be done to strengthen an element, okay. Let us say in a static case, gives a support. Stiffening also can be done for a dynamic case for shifting natural frequencies. Okay. If you stiffen any member, already existing member, using some support, then you will shift the natural frequency, okay, away from wherever it is, and wherever it is causing a problem because some excitation is at that frequency. So, when the excitation sees that natural frequency has been shifted by stiffening, the vibration amplitudes drop. Okay. So, stiffening can be done to shift the natural frequencies also. So, now we have a cylindrical shell and we are going to stiffen it using a ring. Okay, we are going to use a ring to stiffen it. Okay. The ring goes around and it stiffens. Okay. Now, it is a hard connection. Okay. Here the displacement of the shell is equal to the displacement of the ring. Okay. And we know that circumferentially, okay, the displacement descriptor is a cosine n theta or a sine n theta, with n being an integer. Okay. And so, because it is a hard connection, the ring also must have same displacement, must have the same displacement. Okay. So, the alpha 11 for the cylinder and beta 11 for the ring, we will calculate for any one particular type of displacement, that is either cosine n theta or sine n theta, does not matter. Okay. So, now so let us say this stiffener is attached at an axial distance or location x equal to x star, and I will consider u3 to be sine m pi x by L cos n theta. Okay, that is the shape. Okay. So, now I will find alpha 11, okay, the receptance for the shell using this forcing. Okay, P cos n theta delta of x minus x star e to the power j omega t. Okay, and this has units of force per unit length. Okay. So, if A happens to be the radius, then twice pi A is the circumferential length. Okay. So, the total force whatever it may be divided by twice pi A is P, this is force per unit length. Then the delta gives one more 1 by length, and this is force per length. So, the total force unit is force per unit area, which is a must, and this describes a force applied at x equal to x star, and circumferentially it is a cosine n theta. Okay. Circumferentially it is a cosine n theta. So, now what is the Fmn corresponding to this? The Fmn star now, right, is equal to 1 over rho h n mn integral 0 to a integral 0 to L 0 to L integral 0 to twice pi. So, this total length is the L for the shell. Zero to L, 0 to twice pi, P cos n theta delta x minus x star into sine m pi x over L cos n theta a d theta dx. Okay. Now, what does this do? I get 1 over rho h n m n, then the delta will pull out the sine. So, I get an P a sine m pi x star over L integral 0 to twice pi cos square n theta d theta. So, let us look at integral 0 to twice pi cos square n theta d theta. For n equal to 0, this gives me twice pi. For n not equal to 0, I get integral 0 to twice pi 1 plus cos 2n theta by 2 d theta. Now this will integrate to 0 over twice pi, and so I get half d theta integrated, which gives me a pi. Okay, so this is 2 pi when n equal to 0, this is pi when n not equal to 0. Okay. Now let us look at NMN. NMN is again integral 0 to L integral 0 to twice pi sine square m pi x over L cos square n theta a d theta dx. Okay. So what does that do? We have to go to the next page. So I have NMN is equal to integral 0 to L 1 minus cos twice pi mx by L by 2 integral 0 to 2 pi 1 plus cos 2n theta by 2 a. Okay, so this I put dx here and this one a d theta here. Okay, so this gives me L by 2 cos 2m pi x by L integrates to 0 over the length, so this part goes to 0, so I get L by 2 from here. Okay, but here again what I have is this gives me this part, it gives me 2 pi for n equal to 0 and pi when n not equal to 0. So I get L by 2 into 2 pi or pi. Okay. Now for the other part, what did I have? PA sine m pi x star by L rho h, PA by rho h. So I have PA by rho h sine m pi x star by L, and the other part was 2 pi or pi. Okay, and then here I have L by 2 into 2 pi or pi. Okay, so when it's 2 pi, this is also 2 pi. Okay, this part is NMN. When the numerator is 2 pi, denominator has 2 pi. When the numerator has pi, denominator has pi. So they cancel out. So what I get for FMN is 2PA by rho HL sine m pi x star by L. Numerator also has an A. Okay, the numerator, just hold on. So numerator also has an A over here, and denominator also has an A over here. Okay, NMN also has an A over here. So there's an A over here. So this A cancels with that A, and this A goes away. Sorry. Okay, so this, let me mark this. This is my FMN for the cylinder. Okay, cylinder. Now from here we have to get to this lambda tilde mn, which is f mn by omega mn square minus omega square. Okay, and from there we get to eta mn, which is f mn e to the power of j omega t omega mn square minus omega square, and the u3. From here you get u3 as a double sum of eta mn sine m pi x by L cos n theta. So what is that? So we have u3 x comma theta comma t given by 2p by rho h L sine m pi x star by L, that is my f mn, into omega mn square minus omega square into e to the power j omega t into sine m pi x by L cos n theta, double sum over m from 1, n from 0. Okay. Sorry. N is a fixed n. Sorry, just confused the whole issue, I think. So the particular force we have, okay, the particular force we have is of the type cos n theta. Okay, so it will create a response only in cos n theta and no other. Okay, so that's what NMN tells you, that n's have to be matched. Okay, so I hope I didn't confuse the whole issue. So this NMN, okay, what it says when we make it sine square m and cos square n is that only the same mn will give a non-zero value. Okay, so there is no summation over n here because we are exciting at cos n. Okay, so now given this situation, what is u3 at x star theta comma t? That is sigma m twice p by rho h L sine m pi x star by L squared. Okay, because this also becomes the same, cos n theta e to the power j omega t by omega square mn minus omega square. Okay. So now what is alpha 11? What is alpha 11? Alpha 11 is, we divide this, okay, we divide this by p cos n theta. So if we do that, alpha 11 becomes sigma over m from 1 to infinity 2 by rho h L sine squared m pi x star by L by omega square mn minus omega squared. That is your alpha 11. Okay, for the cylinder. for the cylinder. Okay. So, given that this forcing was at cos n theta, okay, the forcing was given at cos n theta, what I should have done is chosen a cos p theta, then shown that if p is not equal to n, fmn is 0. Okay, so p p has to be n, okay, in order for the response to happen. Then when we come here, there is no summation over n because p has to be equal to n. Okay, I am just explaining why there is no summation over n over here, because fmn is 0 when n is not equal to p. Okay, fmn, this fmn is 0 if n is not equal to p, if cos p theta is not equal to cos n theta. So, there is no summation over n. Okay. So, now we have alpha 1 1 for the cylinder. Okay. So, next we go to the stiffening ring. For the ring that stiffens, okay. So, we have a ring over here which is actually a one dimensional structure. Okay. So, it also will have a radius of a, then it will have a width of b. Okay, this width is b. Okay, then there is a thickness of the thing, there is a small thickness. Okay, that thickness, or we call this cross section the area A. Okay, this thickness into this, okay, this area, yeah, that area we call it area of the ring. Okay, so what is the volume of the ring? Area of the ring into twice pi a is ring volume. Okay. Similarly, what is the shell volume? Shell volume is twice pi a into the thickness into the length. You will need this later, that is why. Okay, you will need this. Now, for the ring, being a one dimensional structure, we have to find beta 1 1 for it. So, the Q3 that is going to be applied has to be again cos n theta. Okay, this P cos n theta e to the power of j omega t. Okay. Now, here because it is a one dimensional structure, P has units force per unit length, force per unit length. Okay. So, now, so there is a cos n theta force that is actually applied on the shell, on the ring, sorry. Okay. So, the what is the Fn now? Okay, there is no m index here, it is 1 over rho, not h this time, rho a. Okay. Then no more nmn, n of n. So, that is the difference between 1D and 2D, two dimensional structures. Right from the beginning this difference was there. Okay. Right from Hamilton's law this difference was there. We are throughout seeing 2D structures, 2D surfaces where it is mass per unit area and force per unit area. The moment you come to 1D, it is mass per unit length and force per unit length. Okay. So, here this part has to be mass per unit length instead of rho h. Okay. So, what is the numerator? Numerator is 0 to twice pi p cos n theta into n theta. So, basically if I put cos p theta, which is the mode of the ring, and integrate, then this will be 0 as long as n is not equal to p. Okay. And so, this has to be equal to n. Okay. Now, what happens over here? So, n of n is also integral 0 to twice pi cos square n theta a d theta. Okay. So, this is equal to twice pi a and equal to 0, this is equal to pi a and not equal to 0, and so is the numerator. So, is this numerator. So, what we get here is that f n is equal to p by rho times area of the ring, and I either get twice pi a or pi a, and I get twice pi a or pi a. So, this cancels out. So, this is equal to p by rho a r. Okay. We are just about out of time. So, what I will do is I will stop here and continue in the next class from here. Thanks.